The question says that a steel wire of length 4.7 meter and cross section area of 3 into 10 raised to the power minus 5 meter square stretches by same amount as copper wire of length 3.5 meter and cross section area of 4.0 into 10 raised to the power minus 5 meter square under a given load. What is the ratio of Young modulus of steel to that of copper? So here there are two specimens. One is of copper and one is of steel. Now they both have different length. The steel wire is of 4.7 meter long and copper wire is of 3.5 meter long, and they both have different cross sectional area also. The steel wire has this cross sectional area and the cross sectional area of copper wire is 4 times 10 to the power minus 5 meter square. Now under a given load they both undergo the same amount of deformation, that is delta L, or the change in length is same in both the cases. Now we have to find out the ratio of Young's modulus of the steel. So we know that Young's modulus is the ratio of the stress to that of the strain. Now for elastic limit, till elastic limit, we know that this Young's modulus is constant as per the Hooke's law. The ratio of the strain to that of the strain under the elastic limit is constant, and that is known as the Young's modulus. So and we also know that stress is defined as load per unit cross sectional area. We have to find out ratio of Young modulus of steel to that of copper. So upon formulation of this Young's modulus of steel to that of copper, we write Young's modulus of steel in the numerator, that is the stress in the steel wire divided by the strain in the steel wire to that of the stress in the copper wire to that of the strain in the copper wire. Now we can further simplify the stress as load per unit cross sectional area of steel multiplied with the inverse of the strain, that is L by delta L. Here delta L is the change in length, and we know that delta L for steel and delta L for copper is both equal, so they both will result out to 1. The ratio of delta L of both will result out to 1, and we also know that load given to the both the wires are same, so this will result out to 1 as well. Now upon further simplification, we get the ratio of the Young's modulus of steel to that of copper to be equal to the cross section area of copper multiplied with that of steel divided by cross section area of steel multiplied with copper. So upon solving, we get the ratio to be equal to 1.8. Now when we use these real values of Young's modulus of steel and divided with copper, we also will get the value similar to 1.8. So the ratio of Young's modulus of steel to that of copper is 1.8 as calculated. Thank you. The question says that figure 8.9 shows the stress strain curve for the given material. What are the Young's modulus and approximate yield strength of this material? So by definition, we know that Young's modulus is the slope of stress strain curve under elastic limit, and we see there that the elastic limit is somewhat over here. Now we can take slope from any part of this plot before this line, before this point, that is 3 into 10 to the power 8 Newton per meter square. So let us take a point where we can get the value of a stress and its corresponding strain to exact value. So we select this point, that is 150 into 10 to the power 6 Newton per meter square, and its corresponding strain is 0.002. So upon division, we get, by finding the slope, that is dividing stress by strain, we get a value of 75 into 10 to the power 9 Newton per meter square. And to find the approximate yield strength of this material, we see that the straight line deviates at this point, so we can say that this is the yield strength of the material, approximate yield strength of the material. So its yield strength would be equal to 3 into 10 to the power 8 Newton per meter square. Thank you. The question says that the stress strain graph for material A and B are shown in figure 8.10. There is this figure, and we have to find out, the graph are drawn to scale. We have to find out which of the material has a greater Young's modulus and which of these two material are a stronger material. So as per the definition, we know that the strong material is a material which can respond to a greater stress as compared to the other material, and Young's modulus is the slope of the stress and slope of the stress strain curve under elastic limit. So if we compare the stress strain curve of these two graphs, then we can get the Young's modulus, which one is greater, and if we compare the highest stress that the material can reciprocate to, then we will get the stronger material. So we will use this scale to find out these two values. So let us first compare the slope of the first graph. So this 78 degree gives the approximate slope of this stress strain plot in the case of plot A. Now if we compare it with that of B, then we see that the slope of B is less than that of A. So obviously we will say that material A has got greater Young's modulus. So the answer of first question is going to be of material A. Now the second question is which of these two are the stronger material. So now we have to compare its maximum stress. So let's make the stress to a scale to the horizontal. Now if we compare these two material, then we see the material A has got higher stress than that of the material B. So we can say that again material A has got higher strength than that of B. So in both the cases, answer is going to be A. Thank you. The question says that read the following two statements below carefully and state with reasons if it is true or false. Now the first statement is Young's modulus of rubber is greater than that of steel. So we have got here the stress strain plot of rubber, and this is for steel. So we know that Young's modulus is the slope of the stress strain plot under the elastic limit of the material. So we see here that both of the stress is on the same scale, and the slope of steel is way higher than that of the rubber. So we can clearly say that the Young's modulus of steel is greater than that of the rubber. So this statement is false. Now in the second statement, we have stretching of coil is determined by its shear modulus. So for this we have a representation of a coil over here, spring coil. Now let us draw the cross-sectional area. So in this spring we see that either tensile or compressive force acts in the middle way. Now if the force is acting in either horizontally, either it is compressive or it is tensile in nature, the force on the cross section is going to be across the area, or it is parallel to the area. It is not going vertically up or down the area. Like if we consider a rod and it is in tensile force, so the stress here is longitudinal stress. Now this is not the case over here. The force is acting parallel to its cross-section area. That is why we see that the shear modulus is more important over here as compared to the Young's modulus. because Young's modulus is only considered in the longitudinal direction, as where a shear modulus is concerned where the shear force is acting. So here we can say that though there are other forces acting on the spring, but the shear force is more dominant in nature. That is why we have to consider shear modulus over here. Thank you. The question says that two wires of diameter 0.25 centimeter, one made of steel and other made of brass, are loaded as shown in the figure 8.11, this figure. The unloaded length of steel wire is 1.5 meter and that of the brass wire is 1 meter. Compute the elongation of the steel and the brass wires. So given this loading condition, we have to calculate the elongations of the steel and brass wire. Here steel wire is carrying both the loads, that is the 6 kg load of here and 4 kg load. So together it is carrying 10 kg load, and the brass wire is carrying only 6 kg load over here because gravitation force is acting on 6 kg load, and this brass wire is lifting just 6 kg load and steel wire is lifting both the loads. Now here the weight of brass and steel is not considered, so we will not consider that in our calculation. Diameter of both the wire is given. Diameter are same, the length is different. Now from the data book we will be getting the value of Young's modulus, so that we can relate the load with the deflection, load with the elongation. So Young's modulus is defined as load by cross-sectional area divided by the strain, or the stress divided by strain, and from that we can get the delta L, that is the elongation. So we will use this equation in calculating both the deflections, both the elongations. So upon calculation of elongation for steel, we use 10 kg of load here, so we get elongation of 1.5 into 10 raised to the power minus 4 meter, and for brass we get using the same formula, using this 6 kg load, we get 1.3 into 10 raised to the power minus 4 meter. Thank you. The question says that the edge of an aluminum cable is 10 cm long. One face of the cube is firmly fixed to the vertical ball. The mass of 100 kg is then attached to the opposite face of the cube. The shear modulus of aluminum is 25 gigapascal. Now what is the vertical deflection of this face? So it is said that one of the side of this aluminum cube is fixed to the wall and other side is subjected to a load of 100 kilogram. Now we have to find out this deflection, that is the delta x that will happen when it will shear. So we have been given the shear modulus, that is 25 gigapascal, and we have to calculate delta x. So we know the formula for shear modulus is G is equals to stress, that is force, divided by cross-sectional area divided by delta x divided by L, or the shear strain. So here we have been given the load, cross-sectional area, and the value of G of this aluminum, and we have to calculate x, delta x. We have also been given the value of L, that is the edge length. So upon using this formula, we get a value of 4 into 10 raised to the power minus 6 meter. So the shear that will happen, that is the deflection of this face, is equal to 4 into 10 raised to the power minus 6 meter when the cube is subjected to this loading condition. Thank you. The question says that 4 identical hollow cylindrical column of mild steel supports a big structure of mass 50,000 kilogram. The inner and outer radii of each column are 30 and 60 centimeter respectively. Assuming the load distribution to be uniform, calculate the compression strain of each column. So here the question is that the 4 legs are lifting this column of 50,000 kg. Now these 4 legs would be lifting it symmetrically, that is, all these 4 columns would be carrying an equal amount of load of this column. So each of them will carry an approximate of 125 kilogram. Now we have to calculate what is the compressional strain. Since all the legs are in compression, so we have to calculate the longitudinal compression strain. For this, we know that the formula that we have to use is, again, Young's modulus is equals to stress, that is load or force, divided by cross-sectional area divided by strain. Now since strain can be found out as strain equal to force divided by area multiplied with Young's modulus, so we will be using this equation. So here we have been given the cross-sectional area. We can calculate the cross-sectional area by first taking the area of circular region of the bigger radius, and then subtracting it with the smaller radius, like this. Now the cross-sectional area is 0.85 meter square. So we have been given the load, that is 125 kilogram multiplied with 9.8 meter per second square. So that will be the load, and Young's modulus for we will be using Young's modulus for mild steel, and that has a value of 2 into 10 to the power 11. So we get to know that strain is 7.2058 into 10 to the power minus 7, since it is a dimensional quantity, as it is found out by delta L by L. Now they both are in meters, so it becomes a dimensionless quantity. So this is the answer. Thank you. The question says that a piece of copper having a rectangular cross section of 15.2 millimeter cross 19.1 millimeter is pulled in tension with 500 Newton force, producing only elastic deformation. Calculate the resulting strain. So the cross sectional area of this copper block is of 19.1 millimeter cross 15.2 millimeter. So we have to calculate that when it is pulled in tension, how much is the strain. So we know that Young's modulus is equals to stress, that is force, divided by cross sectional area divided by strain. Now strain can be given as load, that is force, divided by cross sectional area multiplied with Young's modulus. Now here we have been given load as well as cross sectional area as well as Young's modulus, so it is easy to calculate the strain, and we get a strain of the value of 1.27 into 10 to the power 3. And now this strain is elastic in nature as given in the question. So this is the final answer of this question. Thank you. The question says that a steel cable with a radius of 1.5 centimeters supports a chair lift at a ski area. If the maximum stress is not to exceed 10 raised to the power 8 Newton per meter square, what is the maximum load that the cable can support? So here we have been given the limiting stress value, that is 10 raised to the power 8 Newton per meter square, and we have to calculate the maximum load that the cable can carry given the cross section radius of the cable. So we know that stress can be related with the load as sigma is equals to force divided by cross sectional area. Now here force is the load and A is the cross sectional area. Here given that it is a circular cross section, so the area can be calculated as pi r square, and force we have to calculate, and here sigma is given, that is the stress, limiting stress is given. So upon calculation we get that the force, limiting force is 7.1 into 10 raised to the power 4 Newton, that is the load should be either less than this or equal to it, so that the steel cable can safely support the chairlift at the ski area. Thank you. The question says that a rigid bar of mass 15 kg is supported symmetrically by 3 wires, each 2 meter long. Those at each end are of copper and the middle one is of iron. Determine the ratio of their diameters if each is to have the same tension. So we have been given that a bar of 15 kg is being lifted by 3 rods. Now the opposite end of the rod have copper wires lifting them, and the middle of the wire is iron. We have to calculate the ratio of their diameters, that is the ratio of diameter of copper versus the iron, given that they are carrying the same load. So, and also they are symmetrically carrying the load, that means the strain in them is same. So we can relate cross-sectional area with load using this equation called Young's modulus. Young's modulus is equals to load divided by cross-sectional area, and that divided by strain. So now load will be equal to Young's modulus multiplied with strain multiplied with cross-sectional area. So we can see here that the load and strain is not depending upon the material. In this case, like the load bear by copper and iron both are same as in given the question. So, and also the strain, the load is being carried symmetrically, that means the strain in the wires are same, that is the elongation in length is also same in the different material wires. So this quantity is going to be constant irrespective of material in this case. So in a nutshell, we can say that Young's modulus of copper multiplied with cross-sectional area of copper, that will be equal to Young's modulus of iron multiplied with cross-sectional area of iron. So we can say in a nutshell that Young's modulus multiplied with cross-sectional area is constant, and when taking the ratio of cross-sectional area of copper with that of iron, we can equate it with ratio of Young's modulus of iron to that of copper. Now, since cross-sectional area is given by pi r square, now to find out the diameter, we can take the square root of this ratio. So upon taking the square root, we come to the conclusion that the ratio should be equal to 1.27. That is, the ratio of diameter of copper with that of iron should be equal to 1.27, so that the given condition of them carrying the same amount of load and to be carrying symmetrically is fulfilled. Thank you. The question says that 14.5 kilogram mass fastened to the end of a steel wire of unstretched length 1 meter is whirled in a vertical circle with an angular velocity of 2 revolutions per second at the bottom of the circle. The cross-section area of the wire is 0.65 centimeter square. Calculate the elongation of wire when the mass is at lowest point of its path. Now here we have to calculate the elongation of the wire. Now for the elongation of wire, for the calculation of elongation of wire, we need to know the Young's modulus of the wire, and the material for wire is steel wire. So according to the formula of Young's modulus, y is equals to the stress induced divided by longitudinal strain, that is delta L by L. Now we have to calculate delta L over here. So we need to know stress in the string, and original length is given and Young's modulus is given in the data. So we will take this information from the data, and we need to know stress over here. For the calculation of a stress, we need to know the load or the tension in this case, and the second thing that we need to know is the cross-sectional area. So stress is defined as load divided by cross-sectional area. So we need to calculate here a known thing, that is load. So for calculation of load, we will apply the equilibrium condition in the vertical direction. Now in the downward direction, we have got two forces, that is the gravitational pull, which is equivalent to mass into acceleration due to gravity, mg, and centripetal force, which is equals to m omega square r. Now here omega is given, that is 2 revolutions per second. We need to convert it into radians per second, and it comes out to be 12.5 radians per second. So this will give us the tension in the string, and it comes out to be 2407.73 Newton. So in this quantity, stress quantity, we know the load, that is tension, and we need to divide it by cross-sectional area, that is this area. Upon conversion in meter square, we will get the stress in the SI units. Now when we got the stress, we will use this Young's modulus of steel to calculate the delta L quantity over here. So delta L can be calculated. This is the stress in the string, and L is given. So delta L is calculated to be 1.85 into 10 to the power minus 3 meter. So this is the elongation when the mass is at the lowest point in the vertical circle. Thank you. The question says that compute the bulk modulus of water from the following data. The initial volume is given, the pressure increase is given, the final volume is given, and we also need to compare the bulk modulus of water with that of air at constant temperature. And the constant temperature is given such that we can assume that the air is not expanding, and explain it in simple terms why the ratio is so large. That is the ratio of bulk modulus of water to that of the air. Now we know by definition the bulk modulus is defined as the pressure over the fractional change in volume, and for fractional change in volume we have been given initial and final volume. So delta V is known, initial volume is also known, and the pressure is also known, that is of 100 atmospheric pressure. Now atmospheric pressure is defined as 1.013 into 10 to the power 5 Pascal. So upon calculation of this expression, we will get the bulk modulus of water, and we have calculated it as 2.026 into 10 to the power 9 Pascal. So here the unit of water that is given in liter needs to change in meter cube. So we have changed it over here. Now in the second part of question, as it was said that we have to compare the bulk modulus of water with that of air. So bulk modulus of air is 1 into 10 to the power 5 Pascal, and the ratio comes out to be 2.026 into 10 to the power 4. So this massive ratio can be attributed to the intermolecular distance of water as compared with the air. Air molecules have much larger distance as compared to that of the water molecules. That is why the bulk modulus of air is so low, or it is much easier to compress the air as compared to water. Thank you. The question says that what is the density of water at the depth where the pressure is 80 atmospheric pressure, given that the density at the surface is 1.03 into 10 to the power 3 kg per meter cube. Now here we see that, let us assume that a volume of water of 1 meter cube is brought to a depth where the pressure of water is 80 atmospheric pressure. Now we have to calculate how much density of the water would be. So on the surface as well as on the depth, in the depth of the ocean, now in the surface as well as in the depth of the ocean, the main thing that is going to be constant is the mass of water. If we have taken initial volume of the water to be 1 meter cube, now the mass of water at the surface would be 1.03 into 10 to the power 3 kg, and at below the surface where the depth at the depth where the pressure is 80 atmospheric pressure, the mass would be same. Now we have to calculate the delta change in volume over here. So bulk modulus is defined as P over delta V by V. Now we have been given the initial volume, that is V, of 1 meter cube, and we have been given pressure, that is 80 atmospheric pressure, and one atmospheric pressure is 1.03 into 10 to the power 5 Pascal. Now bulk modulus of water is also known, that is 2.2 into 10 to the power 9 Newton per meter square. Now we will calculate this for delta V. Now upon calculation we get delta V as minus 36.8 into 10 to the power minus 4 meter cube. Now this much volume is contracted, so this much volume is diminished from 1 meter cube. So the diminished volume, the final volume is 0.99632 meter cube. Now since we know that the mass was same, mass has remained same and volume has contracted, so new density is going to be mass over volume. Mass as the previous one and volume, that is the final, that is new one. So upon division we get the final density of water as 1.034 into 10 to the power 3 kg per meter cube. Thank you. The question says that compute the fractional change in volume of glass slab when subjected to a hydraulic pressure of 10 atmospheric pressure. Now here two things are important. The first is fractional change. Now we define fractional change in volume by change in volume delta V by V. So it is known as the fractional change in volume. And the other thing is that 10 atmospheric pressure, if we convert it into SI unit, then 1 atmospheric pressure is equals to 1.013 into 10 to the power 5 Pascal. So 10 megapascal would be, so 10 atmospheric pressure would be 10 into 1.013 into 10 to the power 5 Pascal. So bulk modulus, here we have to talk about bulk modulus because the volume is contracted over here. So bulk modulus is defined as the applied pressure over the fractional change in volume. Now we have to calculate this quantity, and we have been, as per the data, we have the value of B for glass slab, and we are using it as 37 into 10 to the power 9 Newton per meter square, and we have been given the pressure. So upon calculation of fractional change in volume, we get the value of 2.73 into 10 to the power minus 5. Thank you. The question says that determine the volume contraction of the solid copper tube of 10 centimeter of an edge. Now when subjected to a hydraulic pressure of 7 into 10 to the power 6 Pascal. So here we are talking about the hydraulic pressure being applied on the copper cube. So we will talk about the bulk modulus of copper. So as per the data, we know bulk modulus of copper is 140 into 10 to the power 9 Newton per meter square. Now the bulk modulus is defined as pressure, the hydraulic pressure divided by the fractional change in volume. Now in this fractional change in volume, delta V is the change in volume and V is the initial volume. So we have to determine the volume contraction, it is saying. So we have to calculate delta V, how much volume is contracted. So here upon solving this, as per the given data, we get the delta V, that is change in volume, is upon application of this much of pressure, 7 megapascal, we get it as 0.05 centimeter cube. Thank you. The question says that how much should the pressure on a liter of water be changed to compress it by 0.10 percentage. So the question is talking about compression. Now we know that for this we talk about bulk modulus of the material. Now bulk modulus of water is, as per the data, 2.2 into 10 raised to the power 9 Newton per meter square. Now bulk modulus is defined as the measure of decrease in volume with an increase in pressure. Now here P represents the increase in pressure, and this is the fractional decrease or change in volume. So we have to find out fractional change in volume, how much pressure would be required to cause this much of 0.1% of change in volume. So after converting this percentage into ratio, we get that the change in volume is, the required change in volume is 0.001. Now we know the bulk modulus here, and this quantity is known, delta V by V. Now for unknown pressure, we calculate this, so we will get it as 2.2 into 10 raised to the power 6 Newton per meter square. Thank you.